I'm going to share with you the secret to mental health. Would you guys like to know the secret to mental health? Don't worry about anything. Okay, now it sounds really simplistic, but here you go. So, we've got two types of things in this world that people worry about. Those things that are outside of their control and those that are within their control. Should we worry about things that are outside our control? Absolutely not. There's nothing we can do about it. How many of you guys worry about global warming? Okay, let's ask you, is there anything you can do about that?
Spend our money where companies that actually take care of or think about global warming. Take vacations in places that will be gone in 20 years.
Okay.
Buy my dad's book.
Oh yes, her dad's a climate guy. Okay, so he's paying her tuition, so there we go. Okay.
Yeah, I pay my own tuition.
Oh, okay, very good. So he feeds you. Okay, so back to the story. Always late. Here's the deal. You are 1 out of 8 billion people on this godforsaken rock. Do you think that what you do is going to make a meaningful difference in the outcome? No. Should you worry about global warming? No. Now, let's talk about what's in our control. Should we worry about the things that are in our control? No, don't worry about them. Freaking do something about them, right? Does that make sense? And let's talk about the part of global warming that's in my control. Should I plan to retire to Florida? Hell no, it's not going to be there, right? That's in my control. I'm not going to worry about it. Does that make sense? So, don't worry. Oh my goodness, you can't make yourself any taller or any better looking by worrying. It's not going to happen. Questions? Okay, now let's talk, and I'm going to step back just a little bit into what you've got, the video you guys watched. And I want to talk about this chart here. Can anybody tell me what the safest thing up here is?
T-bills.
T-bills. Why?
Risk-free, U.S. isn't going to default and non-price risk.
Okay, very good. He's saying default risk-free in theory because it's the United States government. And it's got very little price or interest rate risk because of what? What's the difference between the risk in the treasury bills and the long-term government bonds? Is it default risk?
Excess.
Say again?
Excess.
Excess. Okay.
They're very short term. So.
Yeah. So keep in mind this price or interest rate risk, the longer that is, the greater the risk. Treasury bills, 3 months. These long-term government bonds, 30 years. Yeah. Okay, now, can someone tell me why corporate bonds are riskier than government bonds? They have the same, let's say they both have 30 years. Why would corporate bonds be riskier than government bonds?
Corporations are more likely to default than the U.S. government.
Yeah, corporations, and I like the way you put that, because we in theory, the U.S. government's default free, but we know that if you watch the video, hopefully you know that we did default, right, to the French, but that's okay. Anyway, so back to the story. French. We saved them twice after that, so I think we're even. Okay, so the point here is there is default risk in addition to that interest rate or price risk. Now, why are stocks riskier than bonds?
Because then they get paid after bondholders.
Yeah! Who's first in line before shareholders? The bondholders. They get their interest, they get their principal before the shareholders get anything. And so that makes this position at the end riskier. And what's riskier? Large companies or small companies? Yeah, small companies. Typically they're younger. Typically they're less diversified. And they have less, let's call it tribal knowledge or historical institutional knowledge. So there's all sorts of things that can go wrong at a small company that might not even cause a hiccup at a large company. Okay, now we know that risk and reward must go together. That's why these small stocks return like they did and do, and that's why treasury bills return as little as they do. So that's the first thing we could see to let us know that there's a difference in risk here, is the difference in return. The other thing is that roughness of the line. The smoother that line is, the safer it is. The rougher the line is, the riskier it is. And we said it's not just enough for us to talk about smooth and rough. We said we have to have a risk statistic that we can use to talk about this. And we settled on standard deviation. And we know that standard deviation and variance are related. How? Yeah, if we take standard deviation and square it, we get variance, right? So why don't we talk about variance? Why would we talk about standard deviation instead of variance? Say again? Yeah, so you've got standard deviation is in percent, just like our returns. And variance is going to be in percent squared. I have no idea how to interpret percent squared, and I bet you don't either. So that's one of the two reasons. And the other one we'll get to today is the normal distribution. With the normal distribution, you need the mean and the standard deviation. So standard deviation is where we want to be. Now, I gave you a set of returns here. And these are historical returns. And if you ever get historical data, the thing you're going to be sampling, you're going to be getting is sample standard deviation and the sample mean, because we just had a sample of the data. This was like, if you roll the dice 4 times, these were the 4 outcomes. Is that the entire population? No. And so we're going to figure out our sample standard deviation using this. But of course, the first step is to find the arithmetic mean. What's arithmetic mean mean? Yeah, it's just the average, just like your mom would do. She'd add that up, add those 4 things together, divide by 4, and you've got your average. By the way, the biggest common mistake here is people forget the negative, and then they're thrown off for the rest of it. So don't do that. Okay. Now, I think I finished in the video on this slide where I walked through and explained that what we're doing for each one of these years is we are calculating the deviation from the expected return. The expected return is just our very best guess of what the return is going to be going forward. What are we using for our expected return? Say again? Yeah, it's just the historical average, right? The arithmetic mean. And so what we're going to do is subtract that arithmetic mean from each one of these. And so we start out with 0.1370, and we subtract out our arithmetic mean of 0.2144, and that gives us minus 0.0774, and then we square that. And I believe I walked through that at the end of the video, and I told you that I would show you 2 ways to solve this problem. I would show you the hard way and the easy way. Now, I shouldn't have told you that I'm going to show you the hard way first, because many of you will just now doze off. But here's what you need to understand. The technique I'm going to show you here to do the hard way is the technique that you will need to solve the problems in Chapter 11. So pay attention now, and I'll do it again then, and then hopefully, since you'll have seen it twice, you'll actually have it. So go ahead and get your calculator out, and let's walk through how to do this. Okay, I'm going to start with putting in my average, 0.2144. I'm going to store that in location 0. Why am I storing that in location 0? Because I'm going to be using it again and again and again. And I hate typing that out, and I hate making mistakes. So here we go. I'm going to take the first one, 0.137 minus, recall 0. Wait a minute, equals. There we go. So that gives us our deviation. Now, what students are tempted to do at this point is to write that down. Wrong. Don't do that. And the other thing that they're tempted to do is to work down. I'm going to tell you that working across is the smart way to go about it. And here's why. The very next thing we're going to do, we are going to square this thing. And that gives us this number here. Now, when we get done, we're going to add all these squares together. So what do you think I should do with this number right now? Store it. Now I'm going to store it in location. Any guesses? 1. Very good. Store 1. I'm going to clear it. .358. What should I do next? Minus, recall, 0 equals, and what should I do with this number? Square it. And then what should I do with it? Store 2. Very good. .4514. What do I do now? Minus, recall, 0 equals. Then what do I do with that number? Square it. Now I want to point something out to you here. That was actually just .237. When I take a 3-digit number and square it, I get a 6-digit number. When I take a 4-digit number and square it, I get a 8-digit number. That's the way it always works. Okay, so I've got this. What should I do with this number? Store. Where? 3. Very good. And then finally, .0888. What do I need to do right now? Negative. Subtract. Recall 0 equal. Minus .3032. What do I do next? Square it. And then what do I do with that number? Store 4. Okay, now the next step in solving this is to come up with what's called the sum of squared deviations. And by the way, how do we get that? We sum the squared deviations, right? Okay, so here we go. How would I do that in the calculator? Recall 1 plus, recall 2 plus, recall 3 plus, recall 4 equal. So that's our sum of squared deviations. How do I get to the variance from the sum of squared deviations? Divide by n minus 1. What's n? N is the sample size. So n for this would be how much? 4. So n minus 1 is 3. And as I mentioned in the video, that's because of the degrees of freedom. In theory, we used up one degrees of freedom worth of the information in a data set when we calculated the arithmetic mean, right? That's the first thing we calculated. So we used up some of the information. This is how statisticians explain this to me, and I've never been able to understand truly what a degree of freedom is, but this is the correct formula. Okay, now I've got this number. I'm going to, let's see, have I already divided by 3? Yeah, apparently. Okay, what do I do with this number in order to get standard deviation? Square root it. By the way, do you think that would be so cruel as to include that variance number as one of the choices for standard deviation? Absolutely. Right. Okay, so here we go. 0.2413. That is 24.13%. That is the standard deviation for this sample of data. That's the standard deviation for this sample of data. Now, let's talk about how we could go about this in a simpler way. How could we do that? Well, let's do second and then hit the number 7. What does the number 7 say above it? Data. Now, this is one of those places where you can have data hanging out in there that's been there for a long time, and we need to clear that out. So I'm going to hit second and then CE/C, which will clear the work. Now your calculator is set up to do 2 stocks, one versus another. And so there's going to be X and there's going to be Y. We're totally going to ignore Y. We're just going to look at X. So X01, we would put in 0.137, enter. And then we're going to hit arrow down. We are totally ignoring Y. We're just going to totally leave it alone. Arrow down. Now, what do you think I'm going to put in for X02?
0.358.
Yeah, 0.358. Come on, 8. Enter. Arrow down. What am I going to do here? Nothing. Arrow down. What's X03?
0.4514.
0.4514. Enter. Arrow down. What do I do here? Nothing. Arrow down. X04. What are we going to do here?
Negative 0.088.
Yeah, I got to go 0.0888, and then I got to hit the negative, and then what do I do? What button? Enter. And I'm not doing anything here. And I'll click on down to x05 and you can see that there's nothing there. Just because we didn't put anything there, we cleared it up. Okay, now the next thing I want you to do is hit the second button and the number 8. What does the number 8 say above it? Stat. What do you think stat is short for?
Statistics.
Statistics. And then here it says, whenever we hit that, it says LIN. And LIN is either a Chinese lady's name or it can be, yeah, it's short for linear. Now, it's neither here nor there. It does let you know that you're in the right position though. Now, what I'm going to do from here is hit the arrow down key. And what it says is n equal 4. Does that sound right?
Yes.
Yeah. You always want to check this because if here it said n equals 5 or n equals 7, what does that mean? It means we didn't clear out the data in the calculator, right? So always check that one. Now, arrow down. X bar is equal to 0.2144. Does that number look familiar? Yeah, what is that?
It's the
Oh, not quite standard deviation.
It's the
Yeah, it's the arithmetic mean, right? It's that arithmetic mean that we calculated earlier. Now, we can arrow down one more, and it says S sub x. By the way, S sub x means sample standard deviation. So we write standard deviation in a couple of ways. One is like this, and the other one is like this. This is used for populations, and this is used for samples. Do I occasionally get goofy and use this when I'm talking about samples, standard deviation? Occasionally I do. But I'm telling you that this is the correct one. And I want you to notice that this number is the same number that we calculated when we calculated standard deviation doing it the old-fashioned way. If you want variance, if the problem asks you for variance instead of standard deviation, what should you do? Yeah, just hit square, and I'll prove it to you. Here we go. I'm going to hit square, and two things are going to happen. Number one, the number gets squared, and we get that variance we had earlier. The other thing that happened, did you notice what happened to the equal sign? It goes away. And this is your calculator's way of letting you know, hey pal, this is not what I calculated, right? This is not what I calculated. You did some stuff here. This is not the sample standard deviation. And if I click up and then back, whoop, it's back. Now, I'm going to show you something, and I'm going to warn you about it. Some of you will pay attention, some of you will not. When I was a little kid, my mom said, don't touch the stove because it's hot. What do you think I did?
touching the stove.
I touched the stove. This is just the stupidity of the human race, right? Yeah, you're right, Mom, that hurt like hell. Okay, so now, why do I tell you that? Because if you arrow down here, guess what? We've got population standard deviation, but you know, folks, that's not what we're calculating. That's not what we're calculating. Do we have the whole population? No, we've got 4 throws of the dice. We've got 4 throws of the dice. By the way, the whole game here is to try to characterize the probability distribution that this stuff came out of. And this sample mean, the sample standard deviation, is our best, bless you, our best guess for the distribution this stuff comes out of. Okay. So, don't use that. You want to stop right here. You want to stop right here. Don't go any further down. Questions?
I think another example where n was 5, and so as I was doing this, I arrowed down and my n equals 5 is there. How do I do that?
Ah, okay. So what you need to do is go second, and then the number 7, and then go second, clear work. Okay, now try arrowing down and see what your data looks like.
0, 0.
Yeah, you're good to go. Good question. Other questions? I'm glad that you caught that, because that will mess your head up, right? That's the very first thing you should do, is check that sample size, and if it's different, you know you forgot to go back and clear the calculator. Okay, now this all brings us to the normal distribution. You guys have probably heard of the normal distribution before. We also refer to it as the bell curve. But what you need to understand about the normal distribution is it applies to many, 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 many things in this world, including probably the height of adult average, or the height of adult men in the United States. Probably normally distributed. And there are all sorts of other things in nature that are normally distributed. One of them is IQ. What is IQ? Yeah, supposedly a measure of intelligence, right? This French dude back in the 18th, 19th century got a bunch of French school kids together and gave them a bunch of intelligence tests. And then what he did was scored it such that the average child had an IQ of what? 100. That's average. Almost everybody knows that. The thing that very few people realize, though, is that the standard deviation of IQ is 15. The standard deviation of IQ is 15. Now, what can I do with that sort of information? Well, if I know the mean and the standard deviation, I can generate the normal distribution for that group. And so I would say that in the middle there, where you're seeing 11.8% for return on stocks, would be 100 for IQ. Now, so far so good. What does the normal distribution tell us? Well, it tells us about probabilities or percentages of populations based on how many standard deviations away we are from the mean. So, for instance, between plus and minus 1 standard deviation of the mean, we have 68.26%. Between those two things, we have 68.26%. And by the way, on your note sheet, what should you have? You should have this drawing, and then, and I'm a crappy artist, so please just bear with me. Let's see, so we'll call that 0, plus 1, plus 2, plus 3, minus 1, minus 2, minus 3. And so these are standard deviations. So each one of these is minus 1 standard deviation, minus 2 standard deviations, and so on. Okay, now what we have is we can break this thing down into chunks. And we know that 68.26% fall in this chunk. But for purposes of calculations on exams and homework, typically we are using 68%. It's a little simpler. And so then we have, for plus or minus 2%, up here on the big board, we've got 95.44%. What do you think we do with that one? Yeah, 95%. And so far, it all makes sense because if you round 95.44% to the nearest percentile, you get this. If you round 68.26% to the nearest percentile, you get this. And so down here, between plus and minus 3, what do you think we do? 99%. Now this is where it gets freaky. Does 99.74% round down to 99%? Hell no. It rounds up to 100. But if we did that, there wouldn't be anything left in the tails for you to play with, right? And so that's why this is typically the approximations that you see used in exams and homework. And I have tried to make sure that I've used this in all the exam and homework questions. You may on occasion see a practice question that uses the exact, but none of the answers will be close enough to throw you off, right? You should be able to still pick the right answer on multiple choice. Now, should this be on your note sheet? Absolutely. So I had, I was teaching China EMBA, and every once in a while they would have a Mongolian person would join my Chinese. And I had this Mongolian lady in there, and I gave her a problem that required this in order to be able to solve it. And she called me up during the exam and said, you didn't give me enough information to solve this. And I tapped on her note sheet and I said, yes, I did. And she said, you did not give me enough information to solve this. And I said, yes, I did. And at this point, she reaches out to try to grab my lapels. And I jumped back because I was younger and faster then. And she was really, really pissed at me because she thought I had not given her enough information to solve the problem. Now, she and I are still friends on WeChat all these years later. It's all good. But what you need to remember when you get on the exam and you're like, he didn't give me enough information to solve that, and the problem is about probability, whoop, there's your answer. That's the missing piece, right? That's the missing piece. Okay, so let's get back to IQ. If I told you that there was a group of people who had IQs between 85 and 115, what percentage of the population would that be? 68%, right? Now, if I told you there was a population between 70 and 130, you would tell me that's what percentage of the population? 95%. And if I said between 55 and 145, what would you say? 99%. And it turns out that these standard deviations are the way that we come up with different classes of intellectual thinkers. And so if you're plus or minus one standard deviation, I think you're considered average. If you're, I don't know what the other ones are, but I can tell you this one. What do you think plus 3 standard deviation, or 145? If you are 145 or greater, you are called a genius. And then 70 or below. The old clinical term that was used at the time that the study was written was mentally retarded, right? We would call them developmentally challenged these days, but it's all based on this. How many standard deviations away from the mean you are? Now, so far so good. And you're thinking, oh well, he's always going to throw me plus or minus 1 standard deviation, plus or minus 2 standard deviation. Do you think that's how this works? No. So let's start asking questions here. What percentage of the population has an IQ lower than 85? So the first thing we're going to do is figure out the number of standard deviations we are away from the mean. And to do that, we're going to figure out something called T. And you may also see people use Z. It's the same general idea. And it is x minus x bar divided by s sub x. Now, what is the x in this problem? I asked what percentage of people have an IQ lower than 85. So that's going to be our x. All right, told you I'm still on a little coldness in there. Okay, now, what am I going to subtract? 100, because that's the sample standard deviation. I'm sorry, sample mean. And then what do I divide by? 15. And because that is the size of the standard deviation for IQ. And so I've got 85 minus 100 is minus 15 divided by 15 gives me what? Minus 1 standard deviation. And so that means that we are working 1 standard deviation to the left. Now, there are a couple of ways I can go about this. The first is that I can say, well, there are 68.26% of people between minus 1 and plus 1. Is that information going to help us out? Not directly, right? We have to go from there to other places. So, there are a couple things you need to know. Number one, what percentage is under the entire distribution? 100%. Second thing that you need to know, this thing is symmetrical, right? It's the same on both sides. And so that means that if the whole thing is 100%, what is half of it? 50%, right? And if I know that that 68.26% is symmetrical, how much of it is between 0 and minus 1? 34%. Yeah, 34%. And so 50 minus 34 means how much is left in the tail? 16%. And we could have gone about this in a different way. I could have figured out that everything to the right of that is 84%. And how would I have done that? Well, everything from 0 over is 50%. And then I've got that 34%. I add those together and then I subtract that from 100. And I come up with exactly the same answer. Do I care how you do it? No. And it should actually give you some peace and some joy to know that there's more than one way to get it right, right? And so as long as you can figure out one way that works for you, then you're in good shape. Okay, what if I ask you what percentage of people's IQ was higher than 130?
2.5%.
Okay, she says 2.5%. How'd you get there?
That's what's left between the second and third standard deviation.
So a lot of times what people do is they say, oh, okay, between plus and minus 2 is 95%. 100 minus 95% gives us how much? 5%. But what do they forget to do?
Divide it.
Divide it by 2. And why do we have to divide by 2?
Symmetrical.
There's 2 tails and they're symmetric, right? So we can divide by 2 and find out that it's 2.5%. Okay, now I'm going to ask you, so by the way, you've got an IQ of 145. You are a genius. You feel pretty good knowing that you're a genius? Let's talk about what percentage of the human population is smarter than you. What percentage would that be?
0.5.
Yeah, so we're looking at 0.5. Actually, let's take it all the way down and use the exact. What is 100 minus 99.74%? What is 0.26%? And then what do we have to do? Divide by 2, right? So here's what I want you to do. I want you to get your calculator out. And I want you to take 0.0013, which is 0.13%, which is how much is in that genius and above tail, right? And I want you to multiply it by the number 8, followed by 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. 8 billion. By the way, we've mentioned 8 billion once already in this class. What is it?
Population of the world.
Population of the world. Okay, so when I multiply 0.0013 times the population of the world, that gives me a really good estimate of how many people are smarter than you. So here we go. 10.4 million. Just moments ago, you were feeling really good because you were a genius, but now you realize that there are 10.4 million people on the planet who are smarter than you. I've got good news. Probably half of those people are somewhere where they don't have electricity or internet, so you don't have to compete with them. So you're really only competing against the other 5 million. Questions? Okay, now why did I go through all that stuff? Because the numbers are easier to think about with IQ, and we recognize what the world population is, and it helps put things in perspective. But now we're going to talk about stock returns. And in fact, the returns that we have up here represent large stocks. In fact, you can go back a few slides and see that the average return on large stocks for the period examined is 11.8%. And because that is our mean, that is also our expected return. That's the center tent post of this thing. Now, if you work out, we're going to work out by plus and minus 1 standard deviation and so on. Can anybody, just looking at these numbers, tell me how much is 1 standard deviation for this distribution?
20.5.
20.5. How did you get that?
I subtracted 11.8 from 32.3.
She did. She took 32.3 and subtracted 11.8. She got 20.5. Now let's prove her work. What if we take 11.8 and subtract 20.5? What do we get?
Negative 8.7.
Negative 8.7. So, and we see that the standard deviation here is 20.5. If I add another 25.5 to 32.3, I get 52.8. And I get on up to 73.3 if I add another one, and then I can work my way down the other way. Now, I will tell you this about stock returns. We pretend that stock returns are normally distributed. For this class purpose, you will always assume stock returns are normally distributed. But I'm going to tell you 2 things that we know, or one thing that we know and one thing that we suspect. The thing that we know is that stock returns are actually truncated on the left-hand side. What's the lowest stock returns can ever be?
Negative 100%.
Negative 100%. Because of limited liability, the worst that can happen to you is that your stock price drops to 0, which would give you a return of negative 100%. Now, can you go higher than 100%? Absolutely. In theory, we could go to infinity, right? But we know there's no way we can go under minus 100%. So the first thing we know is that this is truncated, meaning chopped off. So it's not truly symmetric. The second thing, the thing we suspect, is that the distribution of stock returns has fat tails. Fat tails. I heard at least one or two people laugh about fat tails. Fat tails in statistics, what does it mean? It means that we have too many observations out here in the tails, and not as many observations as we would expect in the middle if this thing were truly normally distributed. Now, when finance people start talking about how our stock return distribution has fat tails, the statisticians tell us, you guys don't know crap. And here's the reason they tell us we don't know anything. They say that you only have stock returns going back to 1926. Your sample is too small for you to know whether this thing has fat tails or not. And I suppose that's a fair criticism of our work. On the other hand, this is a finance class, and so I get to tell you that you should assume that stock returns are normally distributed. Okay, so now what do? We can answer all sorts of fun questions. Like we can say, what are the chances that you won't lose any more than 8.7%? Oh man, there's a lot to unpack there. What are the chances you won't lose any more than 8.7%? So when I say lose 8.7%, what is my x that I'm talking about? Lose 8.7%. Is it just 8.7? No, it's negative. Minus 8.7%. And then I'm going to subtract out the average or expected return, which is 11.8%. And I'm going to divide by the sample standard deviation, which we said was 20.5. And so this gives us minus 1 standard deviation. If I take minus 8.7 minus 11.8, that's minus 20.5. Divide by 20.5 gives us minus 1. Now remember, the way that I said this is what are the chances that we won't lose more than? Here are the chances that we will lose more than. It's everything from this line over. And so you've got to be careful reading this, because what it's actually asking for is what are the chances that we won't lose more than, which is going to be this whole piece over here, from minus 1 standard deviation all the way out to plus infinity, right? Okay, couple ways to go about that. One way we could do it is we could say, well, this whole thing is 100%, and plus or minus 1 standard deviation is 68%. So I know that tail contains 16%, so 32 divided by 2, right? That'd be one way to go about it. I could do the whole 50 minus 34 thing and get 16%, but that would be the amount for the tail. Now that I know that the probability that I will lose more than 8.7% is 16%, what could I say about the probability that I won't lose more than 8.7%? It's got to be 100 minus 16. It's got to be 84%. Does that make sense? So be very careful when you read the problems. First of all, look for words like lose. If it says lose, you need to put a negative down. Secondly, you need to figure out which side of this thing you're looking at. And of course, you also need to figure out how many standard deviations away are you, is this thing that you're shooting for. What are the chances that the stock will return less than 32.3%? Yeah, it's the same thing, right? Because we've got once more, we've got a tail hanging out there of 16%. 100 minus 16 is 84. What are the chances that it won't return more than 73.3%? So we've got 100 minus 99.74, and then we've got to divide by 2. So we're down to that 0.13%. And then we ask, what's the probability that it won't exceed that? It's what, 99.87%? Does that make sense? Okay, now, lots of practice problems for this. Practice, 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 because that's the only way you will get good at it. That's the only way you will get good at it. So, we start by reading, and we say, what is this x that we're looking at? Lose more than 8% is minus 8, right? And then we need to know what our mean is, we need to know what our standard deviation is. By the way, do you think I would be so cruel as to give you a sample of 4 numbers, make you calculate the mean and the standard deviation, and then make you combine that with what you've learned over here to tell me these probabilities? Absolutely. Now that's actually kind of a 2-step problem, isn't it? What should you do when you run into one of those on the exam?
Save it for later.
Save it for later, I like that. Questions? Okay, now, once again, and I can't stress this enough, you're going to have to practice this or you won't get it right. I took probably 3 statistics classes before I could think about this clearly, and it probably took me 5 years standing in front of a classroom to be able to work all my problems without dropping the ball. It's not as easy as it looks. I make it look really easy, but it's not. So you need to practice it. Questions? How many of you have already taken your statistics class? Did they teach you about mean and standard deviation and the normal distribution?
Yes.
Okay, did they teach you about these? Okay, so one question you're probably going to say is, wait a minute, are you going to give us a situation where t is going to be something other than plus or minus 1, 2, or 3? My answer is no. I will always structure the problems so that it's plus or minus 1, 2, or 3. And here's why. I don't want to give you a table, right? I don't want to give you a table that you have to use during the exam. Do you want a table? No. So I'm always going to make it come out even. In the real world, does it come out that way? No. And at that point, if you really want to get down nitty-gritty and figure out probabilities, you should look back at your notes from your statistics class. Or just Google it, which is usually what I do. Because strangely enough, I still forget how to use the tables. Questions? By the way, do you think Excel can do work like this? Yeah, you plug in that t value, but then you've got to know what is Excel spitting out, right? And so you need to teach yourself that if you're going to use Excel. Okay, so far we've talked about arithmetic average, which is just the one that your mom or your grandma would know, and that's just where you add the numbers together and divide by the number of numbers. So that's really, really easy. And it turns out that for this arithmetic average returns, we could have either used percentages or decimals. It just doesn't matter. But I'm going to teach you a new one now that's called geometric average, and this one is new to most students. And the first thing you need to know is this only works for decimals. This only works for decimals. So you're going to convert all your percentages into decimals before you do this, and then you can convert your final answer back to percentage when you're done. Now, it's not easy, but I'm going to break it down into steps. The first thing is to figure out each one of your decimal returns. The second thing is to add 1 to each one of them. The third thing is to multiply all those 1 plus r terms together. And once we do that, then we just take the whole thing to the 1 over n power. What's n? Yeah, it's the number of observations, right? It's the sample size. And then we subtract 1. Now you say, wait a minute. Why am I subtracting 1? Well, you remember back here earlier we added 1 to all these? Well, we have to subtract 1 to get rid of. So let's say the first one was 108%. If they were all 108%, I'd be taking 1.08, or let's see, they were all 8% returns. That means that the price at time 1 is equal to 108% the price at time 0. So that's the way to think about this, is that this is so many percent of the previous price. And so if I had 108%, so 1.08 times 1.08, and then I take it to the 1 over n power, at the end, I'm going to have 1.08. Now, how do I get back to percentages? Subtract 1 and then multiply by 100%. By the way, multiplying by 1 does nothing, right? It doesn't change your answer. Why is it okay for me to multiply by 100%? Because 100% is 1, right? I haven't changed anything. Okay, so let's do a very simple example here. We have a portfolio. And we've got time 0, we've got time 1, and we've got time 2. And we have prices at these different times. And at time 0, it's worth 100. At time 1, it's worth 50. And at time 2, it's worth 75. Now, I'm going to figure out what is my return. So let me get rid of that. What is my return? Can I calculate a return for time 0? No. In order to calculate a return, you have to have the previous period, right? You have to have the previous amount. We don't. We don't have the price for time t minus 1. So we cannot figure a return there. But we can figure a return for here. It's P1 minus P0 divided by P0. P1 is 50. P0 is 100. So what's P1 minus P0? Negative 50. And then when we divide by P0, what do we get?
Negative 0.5.
Yeah, negative 0.50, or a 50% negative return. Okay. Now, I want to figure out now what is the return between time 1 and time 2. To do that, I'm going to take the price at time 2, subtract the price at time 1. What is 75 minus 50? 25. 25 divided by a piece of 1, which is 50, is how much? 0.5. Okay. If I were simply to ask you, what is the arithmetic mean, or the average return for this set of prices, what would you tell me? 0, right? Because minus 0.5 plus 0.5 divided by 2 is 0. Sounds pretty good, doesn't it? Except for one thing. We started out with $100, and now we only have 75. What's the problem?
Compounding.
Yeah, it's compounding. It doesn't take compounding into account. And so what we need to do is figure out what is the geometric average of this, because geometric average does take compounding into account. And so what we can do is come out here, and we can do a 1 plus R. Of course, that's still nothing. So what's 1 plus minus 0.5? 0.50. What is 1 plus 0.5? Yeah, 1.5. Okay, now in order to find the geometric average, what I'm going to do is multiply this number, which is 1 plus R1, and this one, which is 1 plus R2. We're going to multiply them together. And then I'm going to take that to the 1 over n power. What's n? 2. Now, 1/2 power, mathematicians, tell me there's a button on the machine? Square root. Do you think that I will always give you, no. So you're going to need to know how to do this. Otherwise, I'm going to show you on the calculator. So get your calculator out. And so what I would tell you is, when you're putting these numbers in, let's say 1 minus 0.5 equal, I would store that in location 1, and then 1 plus 0.5 equal, store that in location 2. And of course, you're going to have more than that on the homework or on the exam. But when you get done, what you're going to do is say recall 1 times recall 2, and you're going to do that all the way up through recall however many returns you have. Okay, so this is the 1 plus r times 1 plus r term that's inside the boxes. Now I need to take this whole thing to the 1 over n power, and here's how I do that. I'm going to hit this button that says y to the x. Do you guys see that? I'm going to hit that y to the x, and then I'm going to do open parenthesis. I'm going to say 1 divide by, and I'm going to put in n. What is n for the situation? 2. And then what do I need to do? Close parentheses, equal. So now I have 0.866. Now remember, this is a 1 plus r kind of number. So what do I have to subtract? Got to subtract 1. Is it minus 0.134%? No, it's minus 13.4%. Does that make sense? Because we've got to multiply by 100% to get this into percentages. And so we're really looking at, I'm going to go ahead and multiply by 100 here. And this is the number that I get. I'm going to store that in location 1 because we're going to compare it to something that we're going to come up with here very shortly. Now, so does this number make more sense to us? It kind of does. Because if you think of going from 100 down to 75 over a 2-year period, you're basically looking at, on average, falling around 12.5, right? And so this number of minus 13.4, once we consider compounding, makes a whole lot more sense than 0, right? Okay, now, how could we do this with our calculator? I could say second future value to clear out my time value of money. And I could put in, for my present value, I could put in 100 and put in negative present value. What can I put in for future value? 75. Future value. What should I put in for n? 2. And then what should I compute? I per y. Check that number out. Now, let's see if that's the same number that we got previously. Minus, recall, 1 equals. It's the same darn number. Now you say, wait a minute, this is going to be really easy. All I have to do is the beginning and the end. Wrong. Because we're going to throw some extra stuff in here. We're going to also throw dividends in. And we're going to be looking at total returns. And so you're going to need to be able to take that into account too. I'm going to give you a hint about one of the homework problems. It lists the dividends like this. And it looks like this. Unfortunately, in fact, it doesn't have the zeros at all. It starts out something like this. Unfortunately, the decimal point is very, very tiny. And so what do people think? They're like, well, heck, that's a $25 dividend. By the way, what's the likelihood of a $10 stock paying a $25 dividend? Yeah, that's not going to happen. And so what you need to do is realize that there's actually a 0 point out in front of those things. So once again, on the homework, when you're looking at that, go ahead and write a 0 point in front of those dividends, and it'll help you get the answer a lot easier. Once you start including dividends, then it doesn't work to do what we did here with the future value and the present value. Now, how would I, if I were doing this with dividends, what would I do? Well, what I would do is take the current price plus the amount of the dividend, and then divide by the old price. And that's going to give me the total return for that period. So all I gotta do is take 50 plus my dividend, divide by 100, and that's going to, in fact, if I take that, that's going to give me my R. I can add 1 to that. Or how about this? Instead of subtracting the 100 up here like we have been, just leave it out and take 50 plus a dividend, divide by this, and that tells you, this is a bad number. Let's go a different way. Okay, so here at time 0, we've got a price of 100. At time 1, I've got a price of 110 and a dividend of 5. If I'm going to figure out what the total return for that period is, what would I do? I could take 110 plus 5 and subtract 100 and divide by 100. But what if I just take 110 plus 5 and divide by 100? It turns out it actually gives me 1 plus R. Let me prove it to you. If I take 110 plus 5 is 115, minus 100 is 15. 15 divided by 100 gives me 0.15 or 15%, right? What if I don't subtract out the 100? What if I just say 110 plus 5, that's 115, and then I divide by 100, what does that give me? 1.15. That is the easy way to do this. Let's do another example here. $121, the previous was 110, so that's a 10% increase. And we say our dividend went up by $1 here. If I wanted to figure out what is 1 plus R here, all I have to do is take this number plus this number and divide by that number. That's all I have to do. Now, if you don't believe me, go back and prove it to yourself. Take this number plus this number, subtract that number, divide by this number, and then add 1, and you'll get exactly the same number. I have this out on video where you can watch it. In fact, it's on Brightspace where you can go out and watch how to work this problem. It'll make your life a whole lot easier if you'll just learn about adding the price and the dividend divided by the prior price. Now, do I also divide by the prior dividend? Absolutely not. It's always just the prior price. Okay, so let me give you a real-world example here of the difference between arithmetic and geometric average. So we had the financial crisis, S&P 500 fell 30%. It fell 30%. And then I'm watching, this is several years later, I'm watching CNBC, and there's this woman, and she says, well, we were down 30%, and now we're up 30%, so we're back where we started. Is she right?
No.
No, she's absolutely full of crap. Here's why. Think about this. If we drop from 100%, we drop 30%, now we're down to, say, 70. And then we raise by 30%. 70 times 1.3 is 91%. So we're still down 9% overall. So that statement that she made, she was using arithmetic means, and she was absolutely wrong, because arithmetic means do not take compounding into account. Now, remember I told you in this country, if you're a bright person but you can't do math, you become a lawyer. What if you can't cut it as a lawyer? Journalist. Right? I hope someone leaves nasty comments on my YouTube about that. Okay, questions? So let's talk about what's going on here. What questions do these answer? They answer fundamentally different questions. The arithmetic average answers what was your return in an average year over a particular period. What was your return in an average year over a particular period? And if we look here, your average return in a particular year over this period would be 0, right? But if we ask the question, what was your average compound return per year? Then the answer is going to be that minus 13.4%. And so which tends to be more meaningful to us when we're talking about financial markets? It's going to be this geometric average. But when you are calculating standard deviations, variances, correlations, covariances, that sort of stuff, we always use the arithmetic mean. When you're calculating any sort of statistic that uses a mean, it's going to be the arithmetic mean. Now, you should know the two different questions that these answer. And then the second thing says it's probably, the arithmetic is probably too high and the geometric is probably too low. And then we'll get into the whole length of the period here in a minute. But let's talk about why this is. The only time your arithmetic and your geometric average are going to be equal is when you have a standard deviation of 0. Which means if you've got a standard deviation of 0, that means that the return is always the expected return, right? Never deviates. At that point, the arithmetic average and the geometric average are going to be the same thing. But if you have any standard deviation at all, then your geometric average of positive returns is going to be lower than your arithmetic average. And I'll give you an example here. Let's get our calculator out. Oh, come on. Ah, what the hell. Okay, we've got our calculator, and we're going to do 4 years. And the first thing I'm going to demonstrate is if we have 4 years of 8% returns, that the geometric average is going to be 8%. So here we go. 1.08 times 1.08 times 1.08 times 1.08. So that's 4 years of 8% return. Now, what do I need to do next to get geometric average? I've got to take it to the what power? Yeah, 1 over 4. 1 divide by 4, close parentheses, equals, and then what do I need to do? Subtract 1 and then multiply by 100%, and that brings us to our geometric being 8%, which is exactly the same as what, by the way, if I take 0.08 plus 0.08 plus 0.08 plus 0.08 and divide by 4, what do I get? 0.08, right? So at this point, they're exactly the same. But what if I gave you this set of returns? 6%, 10%, 6%, 10%. If I add all that together, I get 16 times 2, 32, divide by 4 is what percent? 8. It's exactly the same, right? The arithmetic average is exactly the same. But the geometric average will not be the same. And I can guarantee you the geometric average will be lower. And here we go. I'm going to take 1.06. Oh wait, did I say 1.06 and 1.10? Yeah. Multiply by 1.1, multiply by 1.06, multiply by 1.1 equals. Now, what do I do to get the geometric average? Going to hit y to the x, open parentheses, 1, divide by 4, close parentheses, equals minus 1, and then multiply by 100, and we can see that our geometric average is now lower than the arithmetic average. And so the geometric average will always be lower than the arithmetic as long as there's any standard deviation, any variation whatsoever. And so that can help you to remember that this geometric is here we go. The geometric of the arithmetic is probably too high, and the geometric is probably too low. Now, when you get into the for longer periods and for shorter periods, it's a very complex discussion. If you are interested in knowing why that is, I have included an academic paper in the folder for Chapter 10. If you have no interest in knowing why that is, just write this stuff on your note sheet. Do you think most of you will make it through your entire lives without having to know why the shorter, longer period? Yeah, and I know most of you are thinking, hell, that's 95% of the stuff that you teach us, right? I can tell you this one's probably not going to be a big deal for you, but if you're interested in that, for instance, Ms. Sago is on our CFA research team. I'll bet right after class she's going to go read that paper just because she is so focused on that, but the rest of you maybe not. Questions? By the way, yeah, go ahead.
Does that hold true if the arithmetic average is negative?
It's a problem, but you know what? We can figure it out. Would you like to watch an example? Okay, here we go. So let's go ahead and write out the numbers because I tend to do worse with negatives. Okay, so our two sets of returns. Actually, we just need the 1 through 4, right? 1, 2, 3, 4. And so our two sets of returns, we've got minus 8%, minus 8%, minus 8%, and minus 8%. Or, so that's return set 1. Return set 2 would be minus 0.06, minus 0.10, minus 0.06, minus 0.10. Okay, here we go. Get your calculator ready? 1.0, let's see, 1 minus 0.08 is 0.92. Now, shortcut here. Is it okay if I just take that to the 4th power? Yeah. So I'm just going to say square square, and we're there. And then I can take it to the y over x, parentheses 1 divided by 4. And we can see that we wind up with basically our geometric average and our arithmetic average both being minus 0.08. So far so good? Okay, now what if we do the other one? On the other one, I'm going to have 0.94 in there twice, so 0.94 squared multiplied by open parenthesis 0.90 squared, close parenthesis, equal, that's 0.71, and now I'm going to take that to the 1/4 power, and I'm going to subtract 1. So, the geometric average was still lower than the arithmetic average. Does that answer your question? Yeah? And you notice when I was talking along there, I said with positive returns, right? Because I wasn't quite sure, but now we've kind of proven it. Now, is this truly a mathematical proof? No. I'm sure that one of you somewhere will be able to figure out some way in which this didn't, but you know, I think it's right. I think it's right. And keep in mind I'm high on cold medicine, so there you go. Questions? Okay, now, we have been talking about individual assets. And so far we've been talking about just the risk and return of individual assets. But in life, is there more than one asset you can invest in? Yeah, and so we need to start thinking about what happens when we hold more than one individual asset together. And if we hold a collection of more than one individual asset, we call that a portfolio of assets. Chapter 11 is all about portfolios. Now here's the fun thing. When I start holding things together as a portfolio, not only is it the individual movements of these things that matter, it's how they move with respect to each other that starts to matter. Because if half your portfolio is up while the other half of your portfolio is down, then the return of the portfolio is actually much smoother than the return of either one of the things that are in the portfolio. So that's why what we're going to get into in Chapter 11. Chapter 11, all the problems that we solved there, instead of being the sample statistics like we did here, We're going to be doing population statistics. We'll be talking about where we know actually 100% of the outcomes. And there will not be a simple way for us to do standard deviation like there was for Chapter 10. Are there any questions? Okay, read Chapter 11. I will see you next time.